In my last video, I recapped a 20 megabyte Rhodyme hard drive inside an Apple Hard Disk 20. Today I'm going to recap the Sony power supply. So I'm just going to jump right in and pick up where we last left off, starting by removing the hard disk. And even before I remove this controller card and the Sony power supply, we can make some very important voltage measurements, and that's why I have my multimeter here and an oscilloscope. Now, if you don't have either of these pieces of equipment, don't worry. You can just purchase my capacitor list at Mouser and recap in confidence that it's going to work. However, I would still recommend at the very least that you have a digital multimeter. You don't have to have a fluke. You can just have a cheap little one, because you want to make sure that you have the right voltages. And I'm going to be showing you that in a few moments here. But basically, after you recap it, you're going to connect the power cord, and before you even connect it to this controller, you want to be able to measure the voltages just to make sure that you're getting something good. You're not getting super high voltage that's going to blow something up. And with a little multimeter, you're going to be able to do that. Now, the benefit of having the oscilloscope is that not only can you measure voltages like you can on the fluke, but you can also see noise. And the reason I am checking for noise is because I know from experience in recapping the 20SC, the SCSI version, that ESR plays a role and can be a problem, and even can affect noise. So I want to make sure that the voltage levels and the noise levels are roughly the same before the recap and after the recap. So I have to take the measurements now before the recap to establish the baseline data that I will compare with once my recap is finished. So I'm going to start by taking off this connector. This is the main connector that leads from the power supply to this controller board, and the controller board in turn powers the hard drive and the fan with 12 volts. Now, even though there are 5 pins here, there are only 4 wires in this connector coming from the power supply, and I know that the pin on the my far left is ground, so I'm going to put in a little test wire here. And these wires I just bought off Amazon. I'll put a link in the test description. You can snip them off and use them however you like. Very convenient. And then I'm going to put another test lead in the adjacent hole. Now I'm going to take a Ziploc bag. Any insulator will do, just to make sure nothing accidentally shorts. Then I'm going to take my Fluke's black probe, put it on the ground, and the Fluke's red probe goes on the other wire that I'm measuring. And that's why it's very nice to have alligator clips if you happen to have a meter, so you can conveniently make connections like this. Now I'm going to switch the power on. We can see on my Fluke, I'm getting minus 5.5 volts. Now, if I leave the ground in place, but pull out this adjacent wire and put it in the very next one over, I also get 5.5 negative voltage. And no, I did not make a mistake. That is actually correct, right? Then I'm going to pull it out and do the next one over. And this time I am getting a positive 4.8 volts. And if you pull it out and move it over to the last one, there's nothing to connect because there is no pin in there. And I put the wire back into the first slot, and I'm going to check it here with my oscilloscope. You can see that it dropped down here. And I can use my measuring cursor to pull it down to that level. And we see it's minus 5.52 volts. Okay, so now let's check change the coupling from DC to AC so we can check the noise. And then I'm going to adjust my time to 10 milliseconds per horizontal division. And then I'm going to bump my volts over here. You can see it's 100 millivolts. One vertical square is 100 millivolts. So I'm going to bump it now. Now it's 50 millivolts. And we can see the noise now. So in other words, the height of one of these boxes, and there's 1, 2, 3, 4, 5, 6, 7, 8 of them, right? One of these boxes, the height of it is 50 millivolts. And it's varying because these noise spikes are ESL, inductive in nature, and they have to do with wire lengths and how long the ground is. So if my ground was super short, probably those spikes would be minimized quite a bit. But let's go into measuring here. And I'm measuring the peak to peak, and here's the value. So you can see that it's varying because of those ESL spikes. I'm saying 50 millivolts, 40 something millivolts, 52, 54. So it's going to vary, but basically 60 went to 70. So it depends upon those spikes, but the actual constant noise, excluding the spikes, is probably going to be maybe closer to 25 millivolts. But this is establishing the baseline for the first -5 volts. So what I'm going to do is I'm going to disconnect. It's going to go away, and I'm going to reconnect to the adjacent -5. And the noise on it looks to be about the same. You've got an occasional ESL spike here and there. Okay, now I'm going to disconnect it again and connect it to the 5 volt, which is actually, we measured 4.8 volts, but basically this peak-to-peak noise seems to be a bit higher. It's jumping all over the place from 40 to 80 based upon what I'm seeing here. But basically we've got this on camera now so we can see how it looks prior to the recap. Now that we've just completed the unloaded tests of the power supply, I'm going to do the loaded tests. This means everything is connected. The hard drive, the fan, I reattach the power supply to the controller board, and I have both the scope and my fluke attached at the same time, measuring the voltage that's coming into the fan. Now there's going to be a lot of noise on here because it's an inductive load. The fan generates a lot of noise, and you're going to see that on the scope here in a few minutes. I know it's about 12 volts, but we're going to verify that right now as I power on. And we can see that the fan is being driven by roughly 12.5 volts. And because the fan is very noisy, we're getting anywhere from 300 to 400 millivolts peak to peak of noise riding on top of that 12.5 volt power in. And checking voltage on the spinning hard drive, I just used my scope to tap the positive side of one of the tantalum capacitors. This was the easiest one to tap. And then the metal frame is grounded, so I just conveniently put the ground here. And on the scope we see that this is the 0 point right in the middle here. So I've got it set on 2 volts per vertical division, so 2, 4, and then half of 2 is 1, right? That's 5. We're getting a very solid 5 volts there. And if I change the coupling from DC to AC, and then change my volts per division vertically to 50 millivolts, then we can see here that the values that it's giving us is anywhere from 80 to 110, but it's going to vary based upon the ESL spikes, of course. So what, 100? I saw 130 millivolts there. But again, this is establishing the baseline prior to recap. There's also a 12 volt point on the hard drive that I've tapped here, same ground point on the chassis, and on this connector here, which is flowing to our stepper motor. There are 4 pins in this connector, and I have attached my scope probe to the bottom one on this side that's closest to the blue connector. And we see I have it set on 5 volts for vertical division, so we're getting about 10.6 volts. If I change the DC coupling to AC, and it's showing us our value here. We're getting 450, 480. I saw 500 there. Now, obviously, you know, my ground isn't so short, so I'm getting more ESL spikes than I probably should, but roughly 500 millivolts peak to peak noise riding on it. We can now proceed to disassembly with the hard drive removed. The next step is to disconnect the fan. And remove the floppy drive cable here. Now we want to remove the metal tray by pushing everything forward, because there's two hooks here. And then we want to carefully lift up and pull him out. Now we want to remove our power connector here. And then we have some screws to remove here, 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 and over here. And we have one over here. Now it's probably a good idea, so you don't lose the screws, to just partly put them back into their respective holes here. Just do a little few twists. You don't need to screw them all the way down. Now we have a screw here on the side and another screw on this side. And then we can pry up here and remove our power connector. And this is attached to a connector on this board, which we can pull out. It's locked. There we go. And of course, to access the power supply, we should remove this connector over here. And then there's a heatsink here with two screws on this side. And then we've got a screw here and then over here. Make sure I don't lose my screws. I'm going to just twist it a little bit and put them back in their previous places. To make sure I don't lose these screws, I'll go ahead and put them back over here. Okay, and we can remove our little cap here from top of this guy, because we're going to replace him too. And here we can see all of the electrolytic capacitors that need changing. And here are all my Mauser capacitors. As I told you in part 1, I actually purchased a number of low ESR and regular ESR capacitors. So what I'm going to do is I'm going to put in all the low ESR capacitors first. Some of them, like the replacement for this big one, there's only one type available. But some of the others have two types. And if there are any problems when I test it, then I need to go back and figure out which one is, the problem one and swap it out. But the reason I'm going with some lower ESR capacitors is because it's always good to go low. It'll keep the capacitors cooler and ensure a longer life. Now, with that in mind, none of these capacitors are polymer. None of them are hybrids or anything super low like 8 milliohms or 10 milliohms or 30 milliohms or anything like that. They are regular aluminum electrolytics. It's just that you can get some in a lower ESR variety. So hopefully I'm going to be able to just use these capacitors, the low ESR versions, and it's going to work right away when I test it, but we're going to see. Now there's no particular order that we need to go in, so I'm just going to start with the big guy first, and that's this one. Now these leads are pretty big, but I swapped out my standard 1.0 millimeter tip for 1.6. I bought the 1.6 optionally, but these guys might be still too big for that. I'm not sure. I'm gonna give it a try once it warms up here. All right, let's give it a go. Well, it was just the right size. It seems to have worked. Wow, came right out. So I'm using my DE5000 LCR meter to make very accurate ESR measurements of the stock capacitor now. And it's showing 91.93 microfarad when measured at 120 Hertz. The frequency that you test at is very important because all of these numbers will change when you adjust the frequency. And it's saying the ESR is 0.6 ohms or 600 milliohms, however you like to say it. So if I press the frequency button, it changes it to 1 kilohertz. And then we can see that the ESR is 400 milliohms and the capacitance drops, which is normal. Changing it to 10,000. Sometimes it will not go up to the high numbers, but in this case it's still going. 340 milliohms, 78.6 microfarads. I don't know if it'll go to 100 kilo. Yeah, it's overloaded. But if I change to resistivity mode, yes, okay. So in resistivity mode, it's saying it's 319 milliohms. It just won't give us the capacitance because on some of these big fat guys, it just won't go up to 100 kilohertz. And then I'll switch it back. And this also goes to 100 hertz, so you can actually get it down even less. Many of the data sheets usually use 120 hertz or 100 kilohertz. So you'll need to consult your data sheets when you're comparing ESR. But the frequency that it was tested at is really quite important. So now I will, well, before I do that, there are some other things that this LCR meter can check. Right now the D is the dissipation factor. And if I press this button here, it gives me the Q, which is the quality factor, 25.3, which is still pretty good for a very old capacitor. ESR at this 100 hertz frequency is 600 milliohms. And then the angle, it has an angle. Minus 90 is usually about what it is. Minus 87 isn't too off. I mean, that's pretty much spot on. And then it goes back to dissipation factor again. So we'll just get rid of this guy. So here's my replacement capacitor measuring at 100 hertz, dissipation factor 0.034. 90.9 microfarad, again within tolerance. If we change to the Q, it's 29, a bit higher than the old capacitor, which is to be expected. And ESR, it's saying it's 600 milliohms, again at 100 hertz. Angle minus 87.9, and then we'll switch the frequency to 120 hertz. And we'll change to ESR. So 500 milliohms, 90.75 microfarad, 1 kilohertz, 380 milliohms, 88.55 microfarad, 10 kilohertz, 340 milliohms, 82.6 microfarads, and it's probably not going to go to 100 kilohertz, so we need to switch it to resistivity mode, and then it gives us 329 milliohms. So very comparable, actually, these readings. And you might say, well, if they're comparable, isn't this capacitor good? Well, I mean, obviously it powered up the other one, so it's still working. But the fact remains that this is old. I mean, really old. 1985 old, folks, and it's 2023 now. And no electrolytic capacitor has eternal life. So even though you get good readings sometimes the capacitors that are very old still fail. And there are various reasons for that, but we're going to replace them with new capacitors. And what we've just shown here is that the data is not shockingly low ESR or anything like that, which is a good thing actually, because if it's too much lower, again, it could cause instability on switching power supplies, although this particular capacitor is high voltage, so it's on the main lines, which really wouldn't matter much. And by the way, this stock capacitor is 400 volt rated, and the replacement is 350. So probably if this was 400 volts, then it would have been even lower ESR, because usually the higher the voltage you go, the lower the ESR goes. But they didn't have one on DigiKey or Mouser for 100 microfarad, 400 volts, so I got the 350 volt, which is perfectly fine for AC mains voltage. So we can see for C109 on our board, it's very clearly marked which one is the plus, which is this side, and then the negative side always has the dot, right? See that little dot there? And as you know, the negative side is pretty obvious on electrolytic capacitors. It says the negative side, the stripe side. So you do not want to put him in like this with the stripe side this way. You want to put him in like this with the stripe going towards the dot. And all of the capacitors that I have in my Mouser cart, I have them adjusted here for the proper lead spacing. so that these big guys are not going to be standing up on their legs because the spacing is wrong. You don't have to worry about that. It's as perfect as the original. So what I'm going to do is hold him in with my finger. And I know some of you have other techniques that you use to do that, but this works for me. So, I mean, some of you bend the leads, and you can do that, but the next person who recaps this in 25, 30, or 40 years is going to have a heck of a time getting it out. So be nice, you know. It makes your life easier to bend the leads, but it makes the person who's recapping in the future a living hell. I've seen some leads that have been bent parallel to the board. I mean, you know, come on now. It makes it a lot more difficult to take it out when you bend the leads. So I tried to leave them in straight because, you know, that's what the factory caps do. They leave them in straight. So thank you, Sony, for leaving them in straight. So I'm going to tack one of them down here, and I should add a little flex to make it easier. Taking a lot of heat here because it's a pretty thick piece of copper I'm soldering him down onto. Next, I'm going to desolder C110 right next to the big guy. And I replaced my Hakko FR301's tip to be the standard 1mm tip now, because these are smaller guys, not quite as big as these guys over here. And he fell right out. So to make this fast and easy, I'm just going to show you 120 Hertz. This is the stock cap I just removed, 4.3 microfarad, 18.8 ohms. And this is the replacement capacitor. Same 120 Hertz, 7.1 ohms, ESR, 4.86 microfarads. Great, spot on. It's supposed to be 4.7. This capacitor is rated at 450 volts because they did not have 350 volts. The stock capacitor is 350 volts. Nothing wrong with using 450, and the ESR is lower as a result. And once again, it's marked very nicely to let us know that the stripe needs to go on the dot side down here. So basically, it's opposite this, right? This side over here is the ground, and this side is a plus, but this is reversed. So we want the ground stripe to be facing the board edge. And we'll apply a little flux. Next, I'm going to do the two capacitors on the daughter card, but the problem is, if we look on the back, we can see that there's no way I can get my soldering iron in there because this guy's in the way. So we are going to have to desolder the daughter card. But I'm going to be using my Hakko FR301 desoldering gun, so that's going to be a fairly easy job. It's not hard or difficult if you have a wick, a copper wick. It just will take you a little bit longer. There we go. And it's very nice and convenient. It tells us C181 is here, C182 is right there. Boom. Boom. Very easy. So here's one of them, 1.3 ohms ESR at 120 Hertz, 88.43 microfarads. It's nominal 100 microfarads. The other stock cap is 88.8 microfarad, ESR 1.2 ohm. And the replacement capacitors, 0.8 ESR, 0.8 ohms at 93.01 microfarads. Well, darn. I didn't realize my camera was off until I had soldered in both of these capacitors. But I think you get the picture of how it was soldered in. Nothing too magical about it, just like I've been doing the others. Just make sure you get the polarity correct. The positive on both is towards the connector. Negative on both is towards the opposite side. And here's the solder side of the board after I cleaned it off with 100% iso alcohol. It took some doing, and I'm not really sure if it's flux or just some special coating that's on the back of these boards. But anyway, after a bit of scrubbing with a toothbrush, it did finally come off. And this is where we're going to solder it back on, but you can kind of see some of that coating. I think most people think it's flux, and maybe it is, but if you look at the solder side of the power supply, it's just, I mean, it's from edge to edge. It's almost like it was painted on there, which is something that's a bit different than flux. It's almost like it's a coating of sorts, and if it is a coating, I wouldn't think you'd want to take it off, but I mean, I have cleaned it off before with no ill effects, so it could just be that they painted it with some kind of flux, and it smells kind of bad too, and it'll stay on your hands long after you've washed, you've cleaned all of it off with alcohol, unless you wear rubber gloves or something. It's not poison, I don't believe, but anyway, the smell stays on your hand for a while. And when we solder this card back on, we want to get him as straight as possible. We don't want to have him touching this. This is an insulator. It's not going to short out, but still, it looks bad to do that. And obviously, if you push it over too far this way, this capacitor is going to hit when we put it back in the case. So try to get it. It doesn't have to be perfectly straight. Could be a little bit bent, but just try to get it as straight as possible when you solder it in. Sorry, I had my camera turned off again, so I couldn't show you the soldering, but here's the aftermath. You can see the pin in the middle does not have a pad. That's why he's the only one not soldered. Here's the other group of pins here. And you can see how I got him on nice and straight. Next, I'm going to do C226. And we see here it says C226. And while these bottom markings are helpful, I actually desoldered these two by accident. C226 is actually these two pads up here, and you can see the electrolytic capacitor marking. So that's my bad, but don't always desolder the pads closest to the text. Be sure to look for the electrolytic symbol, because these are the ones we need to desolder. Didn't even have to press the button on that one. Just fell right out. Here's the stock capacitor C226. 21.62 microfarad, 3.4 ohm ESR, measured at 120 Hertz. And this is a replacement capacitor, 4.5 ohm ESR, slightly higher than the stock capacitor, but that's fine. This is just a general purpose, not a low ESR, very typical for a 22 microfarad capacitor of this voltage rating. And here is C226 that I just soldered in. I'm going to be skipping over the mundane soldering parts now to speed up this video. And next I'm going to be doing C222 and C202. Both of these are 47 microfarad. And here is one of the stock capacitors. Here is the other stock capacitor. And the two replacements are approximately the same. These are slightly lower ESR replacements, but I don't see that to be a problem for these two capacitors. And here are the two caps I just soldered in. Next I'm going to do C210. Here's the stock capacitor, 0.7 ohms, measured at 120 Hertz, 317 microfarads. And here's the replacement, 0.3 ohms at 328 microfarad. And this capacitor is just a general purpose. It's not a specially low ESR capacitor at all. And here's the one I just soldered in, the blue one. And now I'm going to do C209. The stock capacitor measures 583 microfarad at 200 milliohms. And the replacement capacitor is 638.6 microfarads at 100 milliohms. Here's the one I just installed. We're down to the last three capacitors. And these are the three that I have backup capacitors for. So I'm going to put in low ESR versions of these three. If there's a problem, then I can swap them out with a general purpose, slightly higher version. But if the low ESR works, then that's great. I'll start with C214. Stock capacitor 214 measures 1,187.88 microfarad at 100 milliohms. And my low ESR replacement measures 1,053 microfarad. It won't display the ESR. I need to switch to resistance mode, so 60 milliohms. Here's the one I just soldered in, and now I'm going to do C213. Stock C213 is 22.63 microfarads, 1.8 ohm ESR. And my low ESR replacement capacitor really isn't that much lower. It's only 1.6 ohms, 22.77 microfarads. Here's the one I just replaced, and last but not least, we're going to do C215. And the stock capacitor C215 is 449 microfarads, 600 milliohms. My low ESR replacement, 491 microfarads, 100 milliohms, which, if there's any problems, it could be this one. This is substantially lower ESR than the stock one. And here is the fully recapped power supply. Now, all of the capacitors I'm going to show you now, this one, these two over here, and this orange guy back here, these are the only ones that sit flush with the board. They're not sitting up on their legs at all. So you want to make sure that you push the caps down before you solder them so that the bottom of the cap is touching the board. That's what I mean by sitting flush. But all of the other capacitors, which means all of these three capacitors here, the two on the daughter card, and these two here, sit up on their legs. But they are small enough to where that doesn't matter. Now, yes, I got the lead spacing correct, but the way Sony designed this board is such that the leads do not come out of their bodies, spaced 5 millimeters apart. On these two, even though I got the lead spacing ordered at 5 millimeters, they're shaped, right? They stick at, they were shaped at the factory to be 5 millimeters, but they don't come out of the body at 5. They come out of the body at 2 millimeters. So these are going to sit up on their legs. Do not try to force them flush. You're going to break something if you do. So just let them sit up on their legs a little bit, and they'll be fine. Now, the last thing I'm going to say is that this black guy here and this black guy here, they're both capacitors. You probably heard the name Rifa before if you've recapped anything with a Mac. These are not Rifa brand, but they act the same way. They're on the mains voltage side, and they're very small capacitance, and they act as noise filters. I have never heard of these blowing. Rifas, you probably heard of those blowing, but these are not Rifas. So if ever one of these is visibly exploded, then and only then would I recommend replacing them, and you can see the values marked on them. And basically, you can replace them with any X1 or Y2 safety capacitor of the same capacitance value and voltage value. But I'm not going to replace these because they're just fine now. Oh, and I also cleaned off the flux on the bottom of the board. When putting the power supply back into the frame, you want to make sure you get the PCB to align such that the bottom metal protrusion comes through the hole in the PCB here and also over here in this corner. Okay, now it's time for the unloaded smoke test. I'm going to check the first negative voltage here. Ready to power on. 3, 2, 1. Minus 5.5, great. So I'll switch it now. Minus 5.5, great. Minus 4.77, great. And here is the fully loaded test, and everything, the controller, fan, hard disk are all connected. I have my scope probe attached to the same point on the hard disk, which measures 5 volts. So I'm going to power it on now. Here we go. 3, 2, 1. So same voltage as before. Here's the 0.2 volts per division, 2, 4, half of 2 is 1, rock solid 5 volts. And here's the noise writing on the 5 volt line, also set to 50 millivolts just like before, 1 block vertical, peak to peak. Maybe marginally more than we saw before, but not anything too substantial. Again, a lot of these ESL spikes, it depends on the ground point and the length of your ground on the scope probe. So if I had a super short ground connected to, well, maybe something other than the frame, then a lot of these ESL spikes would most likely go away, but I don't see any problems here. And here's measuring the fan, roughly 12.8 volts. And the noise is marginally higher, but again, I think that pertains to my ground wire more than anything else. So no problems here. And we're now measuring at the stepper motor, same 10.6 volts. And roughly 500 millivolts of noise. So again, no issue here. And for our final test, we need to see if it boots the Mac. So we have to power on and let it warm up until the LED stops flashing. And here we go with the Mac. All right. But check this out. We booted the HD20 with a Macintosh 128K. That's right, 128 kilobytes of RAM. You may have heard that this is impossible, but actually it is possible if you have the newer 128K ROMs. So basically this computer is a Macintosh 128KE. E for enhanced. If you have the older 64K ROMs, they don't have HFS in memory, so you would have to load the HD20 in it, but you can't do that with only 128K. You need 512K or higher. But if you have the 128K ROMs, that allows this minuscule 128K amount of RAM to be able to boot the HD20. Neat. Now here's something that's pretty neat. It's a pass-through connector, so you can daisy chain another HD20 and multiple ones if you want to. I only have the one, so I normally don't do that. Instead, I connect my FloppyEMU to this connector here, and that allows me to very quickly and easily move files by SD card. The FloppyEMU makes that super easy, and then I can download from Macintosh Garden, put it on here, and then copy files from the FloppyEMU to the real Rodime drive. Another approach is also to use the Tash20 by Tashtari, sold by KMac Vintage and others. And this one is very frustrating because you can't put the SD card into your modern Mac. However, there is a solution for that if you use the FloppyEMU as an intermediary. And I'll just go ahead and boot with this. So you just plug it right in, and you don't need any external power. So we'll just turn on the hard disk, and then when you flip on the Mac, then the LEDs light to show you that it's powered. And when you boot, it actually boots off of the real HD20 because that's directly connected to the Mac. But as you can see here on the desktop, the Tash20 has 2 drive partitions on it. These 2 are the Tash20, and they have various files on them. And you can copy to and from just like any other hard disk. So basically you can have 3 hard disk 20s when you use the Tash20, but still the Tash20 is very frustrating to use because the SD card doesn't work with modern Macs. And so what I do is I use my FloppyEMU to load it basically by copying files from my FloppyEMU to my hard disk 20, the real hard disk 20, and then I reboot with the Tash20 installed, and then I can copy over those files to the Tash20 partitions and vice versa. So it's a bit troublesome, and I wish it could be updated so that the SD card would work directly with modern Macs, but this is my indirect way to get files to and from the Tash20. Well, overall, this recapping job went much more smoothly than I expected. I didn't expect too many problems on the hard drive in part 1, but for the power supply, I thought, well, maybe at least one capacitor might give me trouble, but hey, all of the capacitors that I chose were just fine and didn't have any problems at all. I must also say that the Hakko FR301 desoldering tool that I purchased made everything much faster and easier. So if you desolder something at least once a month, I can highly recommend this. It's probably worth the price. But if you desolder less frequently than that, then it's kind of an expensive tool. It's maybe not worth it to you. And in that case, I would recommend a copper desoldering braid and or a low-cost desoldering pump. And I've put links to a variety of desoldering tools for you down in the text description below. I also included links to a Mauser cart, which contains all of the capacitors used in the Rodime hard drive recapping shown in part 1, and all of the capacitors I used in this video to recap the power supply. And I included a link to the Noctua fan that I swapped out in part 1. Now, I'd love to hear your comments down below. Some of you had suggested in my previous video that I wasn't holding it long enough, but I must say that when you're using it at 400 degrees, you can just put it on for a fraction of a second and it melts the solder, even on double-sided boards, all the way through. It's just absolutely amazing. Also, some of the portions of the video I sped up a little bit when I was desoldering, so maybe I sped up the part that you didn't see me holding it, but really you don't need to hold it. In my experience, I didn't need to hold it down for even a second to melt all the solder necessary to suck it all out. But again, I'd love to hear your thoughts overall on what you thought of this video. Also, if you like this video, I'd certainly appreciate a thumbs up, and please subscribe if you'd like to see more content like this. Thank you for watching today, folks, and I wish all of you a wonderful week.